In this recording, I'll be looking at the capacitance of a parallel plate capacitor. Most of these problems involve 4 steps. The first step is acknowledging that one of the plates is going to be charged with plus Q and the other plate is going to be charged with minus Q. We have to make that assumption. The second step will be solving for the electric field in between those two plates. The third step will be determining the electric potential between those plates, using the idea that the electric potential is negative the integral of E dot ds, the distance between the plates. And then the last step will be to use our general capacitance formula. Q is equal to Vc, solving for capacitance. Capacitance will be charge over voltage. We'll use these 4 steps on every one of these derivations moving forward. So let's go ahead and take a look at this. We have 2 parallel plates, one charged plus Q, the other one charged minus Q. We have an electric field radiating uniformly across from the positively charged plate to the negatively charged plate. So we've gone ahead and we've established the fact that one of the plates is plus Q, the other one is minus Q. Now we have to solve for the electric field. We're going to use Gauss's law to do this. Now, generally speaking, Gauss's law says that the electric flux is equal to the integral across the surface of E dot dA, which is equal to the enclosed charge over the constant epsilon naught. In this case, we're just going to use this component of Gauss's law, and we will continue on with it, and we'll say that the electric field is constant, and we're going to multiply it by the area of one of the plates, and that's going to be equal to Q enclosed over epsilon naught. Now, really what I'm doing, by the way, is I'm looking at a large plate, and my Gaussian surface is going to be equal to a cylinder in this case. By the way, what I'm really doing is redoing something from one of the previous derivations. This is my Gaussian surface. And I chose a cylinder because if the plate is charged positive, then the electric field lines will radiate both above and below. And they will only be penetrating through, the electric flux will only be penetrating the end caps of my Gaussian surface. And so therefore the area is 2 times the area of a circle. So, so that's for starters. Then I also need to recognize that the surface charge density sigma is going to be equal to the charge per unit area. Therefore, the charge Q is going to be sigma times area. Now, that's going to be important because right over here, I'm going to substitute that in. So this becomes on the right-hand side, sigma times area is equal to, divided by epsilon naught is equal to E times 2 times the area of one of the circles. Now, we know that the area of a circle is pi r squared. I could put that in. But we can immediately see that the variable A is going to drop right out here. As I solve this for E, I get sigma over 2 epsilon naught. Now, again, this is all a review. This is the electric field strength for a single plate. And so if I were to look at a side view of a single plate, if I were to kind of sketch it 3-dimensionally, it might look like this. Then that means that in a parallel plate capacitor, I also have a negative plate. So the electric field due to the lower positive plate is going to radiate away from the positive plate with a magnitude or a strength of sigma over 2 epsilon naught, both above and below the plate, sigma over 2 epsilon naught. And it's uniform. Doesn't matter how far away I get from the plate, the strength of the electric field is the same, sigma over 2 epsilon naught. That's because the plate is sufficiently large, and sometimes we even say infinitely large. If I look at the electric field due to the negative plate, the upper plate, we can see that it is going to be directed towards the plate because it's negative. A positive test charge will be drawn towards it, so the electric field is also going to be sigma over 2 epsilon naught. It's going to be towards the plate here, so sigma over 2 epsilon naught. And then down here, it's also going to be up towards the upper plate. The electric field is sigma over 2 epsilon naught. We can see that outside of the plates, So in between the plates, we have both the electric field components both going up. These cancel out, and I'm left with an electric field strength in between the plates of sigma over epsilon naught. And so this is really the important part of step 2. Step 2 that I've done right here, now that it's done, this is all a review. Everything above this line, for the most part, should be a review from Gauss's law and electrostatics. So here I am, and I'm ready to proceed. Let's go ahead and move on to the next step, which is to basically integrate my electric potential. It's negative the integral of E dot ds. E I now know, so it's negative the integral of sigma over epsilon naught times d, the distance, the separating distance between the plates here. That's just a constant. It's not a variable that's going to be changing. So step number 3 is now done, and now I'm just going to place this into my expression for capacitance. This is my last step. Capacitance is charge over voltage, or in this case, charge divided by, well, I guess I never finished here. So let's go ahead and do that. By the way, I have to substitute for sigma. It's equal to Q over A. So this becomes Q D over epsilon naught times A. So I should have finished this previously. So now I'm going to substitute that into the denominator. And that becomes QD over epsilon naught A. The Q's cancel out, and my capacitance becomes epsilon naught times A over D. And that is my expression for the capacitance of a parallel plate capacitor.